Okay guys, crazy people, this is paleomagnetism and seafloor spreading explanation for GCSE geology. So if we take a mid-ocean ridge, and I'm just going to zoom in here, and we draw out what's happening at a mid-ocean ridge. This is obviously the ocean. At a mid-ocean ridge, you have the process of seafloor spreading. Okay, so what happens at the mid-ocean ridge? This is the lithosphere. It's being thinned and it's pulling apart. Okay, and as the lithosphere thins and pulls apart, what happens? If this is the lithosphere, okay, that's the lithosphere there. The asthenosphere, which is the molten, 5% molten mantle rock, rises up here, and that's the asthenosphere. Now, because the mantle is 5% molten in the asthenosphere here, and the pressure is lower because this part is thinned, in this region here you're going to get melting, and that's going to be called decompression melting because you're taking the pressure off. So if you lower the pressure, you will melt the mantle, and that material will start to rise up as feeder dikes of material, and it will make new rock at the ridge. So if this is the axis of the ridge, if that's the axis of the ridge, new rock is made either side, and as it's made, it will spread away from the ridge and spread away from the ridge. Okay, so new rock is made at the ridge, older rock away from the ridge. So it's old here, I don't know if you can see, old here, and very, very young here at the ridge there. Now, as this process of seafloor spreading happens, what you get, I'll just rub out my young part here, is you're going to get mid-ocean ridge stripes. Okay, so this is volcanic basalt, igneous basalt rock here, getting made at the ridge and then spreading away from the ridge. Okay, so purple here, we're going to call this normal. Okay, so that's normal polarity basalt. Now, what that means, if I just zoom down to here, the Earth has a magnetic field. This is the Earth. Its magnetic field at the moment in the North Pole here, this is the North Pole, this is the spin pole. So the spin pole and the magnetic pole are not quite aligned, so the Earth's spinning this way, anti-clockwise on its axis. That's the spin pole. But if you imagine a bar magnet in the Earth here, magnetic north is actually at geographic south. So that's north for the magnet, and that's south. Now what happens in the Earth is out of the north here, you get what's called field lines. So this magnetic field is shooting out of the Earth here in the south, coming back into the Earth here in geographic north. And this is obviously magnetic south. The bar magnet is the wrong way around. Okay, so these are called the field lines. So field lines. Now that's the current day position. So if you've got a piece of basalt in a rock, so this is your rock, wherever you are on the planet, if the magnetic field is currently south, north, like that, the little magnetic crystals in the basalt as they cool, imagine that's a crystal, will align south, north, okay? So this one will be south, this one will be north. The crystals will align like that, okay? And that's called normal polarity, because its poles are the same as the present day. That's why we call that normal polarity. So in a rock, this will be the normal polarity of the rock, okay? So this will make, at the ridge, a stripe here of purple, normal polarity rock, aligned in the same way as the current field. Now, unfortunately, in the past, the magnetic field lines have been the other way around. They've been north with geographic north and south with geographic south. And then these arrows change around. Everything swaps around the other way. So the field lines start to flow that way. Now, this is what's called a magnetic reversal. So the magnetism has been reversed in the past. Now imagine here, you might see magnetically reversed rock. So instead of the field pointing the way it was, with the present day, it's the exact opposite. And you can use a magnetometer survey in the ocean by towing a boat over to pick up these slight variations in the magnetic field. So these were now going to be reversed magnetic anomalies. This is a reversed magnetic anomaly. And then in the past before that, it might have been aligned normal, just like it is today. So normal there, normal here. And then before that, it might have been aligned reversed, here and here. So what you get is a map of the stripes in the ocean. Obviously the ocean floor just looks black because it's just basalt, but you'll get a series of normal, reversed, normal, reversed, normal, reversed. And what you see is the pattern is symmetrical either side of the ridge, and it's young basalt at the ridge, old away from the ridge. So this is what's confirmed seafloor spreading. If we know that the pattern is symmetrical either side of the ridge, we know that the stripes must have once formed at the ridge and then they've flowed away. And that's what a geologist calls seafloor spreading. And they call the whole model the geotape recorder model because it records where the rocks have been in the past. This rock here was once at the ridge at the same time that that rock was once at the ridge, and then later it spread apart. And there'll be more stripes away from the ridge going on indefinitely until you hit the continent on the other side of the ocean. And this is happening in places like the Atlantic today. So once the basalt cools, if this is the basalt rock, it has to cool down below 570 degrees C, and we call that the Curie point. Okay, so it's spelled Curie point. Okay, so once we get past the Curie point, this is when basalt can become magnetic, and it will store what's called the paleomagnetism and a stripe in the rock, and that helps us confirm seafloor spreading because it's a symmetrical pattern either side of the ridge, and it gets older away from the ridge. 0 million years at the ridge, many million years away from the ridge. Now, if we know the age, so we know that's, say, 10 million years, 10 mega annums, and we know that distance is, say, 10 kilometers, we can use speed equals distance over time to work out how fast the spreading rate would be. So if we just use that formula, speed equals distance, so we know the distance is 10 kilometers, divided by 10 million years, so we know that in 1 million years it's moved a kilometer. So it's pretty simple. We can work out the spreading rate of seafloor spreading if we know the magnetic stripes. Now, if I just rub out the title here, how we actually know all this, just rub out this title, is on a magnetics survey. Imagine this is average magnetism. If we've got a positive anomaly, it's going to go above the line, and if it's a negative anomaly, it's going to be below the line. So at the ridge, there's going to be a slightly positive magnetic anomaly when we tow a magnetometer over, so the magnetism on the recorder would look like that. When we get over a reversal though, it's going against the present field, so you get what's called a negative anomaly. And that's how they map the stripes, positive and negative anomalies. And you'll see either side of the ridge, the pattern will be symmetrical like that. You'll get a symmetrical pattern here of where you have a positive anomaly, and that means the magnetism is normal and it's reinforcing the current field, where here you'll have a negative magnetic anomaly where it's going against the magnetic field. Now they think that a GCSE geologist should be able to understand this, and I think it's quite a hard concept to understand, but as long as you understand that the Earth's magnetic field is currently orientated the wrong way, geographic north is actually magnetic south, and that switches every few million years. So every million years you get about 5 reversals. It just makes lots of stripes in the ocean, and those stripes have different ages and they get older away from the ridge, and that confirms seafloor spreading. You kind of understanding seafloor spreading and positive and negative anomalies. So hopefully that's useful, guys. Any questions, just drop me an email. Cheers.